it's Sandy Kettle here once again from Servo Components and Systems here in the UK. And this video is going to take you through a simple guide to setting up a Copley Zenith amplifier to run a Siner linear motor. So the motor we're going to be controlling is the MLE 5 series, which comes in a wide range and can deliver peak forces up to 2000 newtons, or continuous typically up to 1000 newtons. So this one is the 5. We're going to be running it with a capability of 400 newtons peak, with speeds up to 3.5 meters per second, although there is an HS version which can take you up to 7 meters a second. So consult us for sizing it for you, and we'll get the right one for your application. So to start, we need to run CME2. It's a PC-based program which will connect to the servo drive, and the great thing is it's common across all the Copley drives, so once you've learnt one, you've learnt them all. But here we're connected to an XP2 drive, and the first thing you're presented with is a block diagram showing the motor, the I loop, the V loop, P loop, and various other options there. But first of all, we have to select the motor type. So in this case, it's a brushless, it's linear. We don't have any halls because in this case, in this instance, we've got a BIS-C encoder, which is serial data and clock, no mod sign, no sign cos rather. So it's all done with serial communications. So very, very fast, as we'll see in a moment. And then we need to enter the motor details, and all this can be obtained from the Siner data sheet that comes with the motor. And the most important thing is we've got a cycle length of 24 millimeters, and that's important when we come to commutate the motor. Once all this information has been entered, then we can merely press the calculate button, and it will give us a set of parameters which will get you close to the tuning required. We can then go in manually and tweak it if required. Now, one thing we have to do is to set up the BIS encoder in this case. Really, all the encoders, all the serial data encoders are very much the same. It's a bit like whether you speak French or Spanish or English. They all have their little nuances, and it's really to up-specmanship each other, really. But the problem is, when you have a variation of standards, you need to know how many bits you've got in the data stream and the resolution, etc. So for us, we know that the encoder has 32 bits, but it also has 2 extra bits, and that's defined in the advanced settings. And the advanced settings are shown here, where we've got an active low error bit and a warning bit. So really, we've actually got 34 bits altogether, but these have to be these have to be specified. And the other complication is, or variance, is that we can have different order of data. So you can have position, alignment and status, or position, status and alignment, or a number of others. And you have to tell it what order the data is in. But we can do all that for you. And you need to select the baud rate. In this case, it's 2.5 megahertz. And what I didn't mention is that the actual resolution is 1 micron. And here I'm actually showing the actual options you've got for the format order. Not quite as I said earlier. Now the next thing you should really do is configure the encoder and check the phasing. And there is actually a function for that called auto phase, and that will go through a procedure for phasing the motor. But once you've done that, you can then get into tuning the motor. And these are the settings. This is the I loop, and to check that you're happy with it, you can go to the scope and confirm that the response is what you'd expect. And here's my response here. So it's pretty good. The commanded current is in the purple, and the blue is in the actual current. So it's following it quite nicely there. Then we would go on and set the velocity loop, and here you can see is my manually tuned values, and I'll show you what the response for that is now. So here is the initial response, and I want to try and get rid of that little kink at on the front of the acceleration there. So I started increasing the VP and VI to try and reduce that wiggle at the front there. Which I've reduced it somewhat, and I'm now showing the velocity error, so you can see that during the majority of the move at constant speed, the error is virtually zero. It's only during the acceleration deceleration which you would expect. And here's a close-up of that move. Here I added the actual current to the plot, just to make sure that we remained in the limits of the drive, and as you can see, we're well in at this stage. So then I moved on to the position loop, and here are the initial values, and monitoring the commander position and the active load position, you can see that it reaches the required position within 100 milliseconds or so. So I've increased the amplitude, or the distance that the drive moves now, and I've also shown the limited position, which is in black. The limited position is the one that's dictated by the actual trajectory limits, the acceleration and so on. So you can see there it's following it precisely. And here you can see I started to increase the maximum acceleration and deceleration. So it's increased the steepness of the curve there. And zooming in on that, you'll see that it's closed the gap there after what's that point? So 200 milliseconds. It's very stable. So it's quite good response there. And so here I've added the following error now because I want to make that zero, basically. After a certain time, I want that to be zero. So I will now go and tweak the gains and see if I can get that closer to zero. But first of all, if I zoom in, you can see that it's actually got a following error of around 30 counts or so. Ideally, I'd like that to be zero. So in this case, I've increased the PP from 1000 to 1200, and now you can see that we've got the orange line settling on zero, which is exactly where I want it to be.